Good evening, sir.
Go- uh, Good evening. We'll start
Oh,
in 2 3 minutes. We'll let people join.
sure, sir. Okay, sir, no problem.
So I think we'll start. Uh, Let people join later. So if you have any doubts, you can ask, or else I'll go through the problems which I prepared. Okay then. So not uh, Give me a second. I'll join. I have some technical issue. I'll join now. Okay. So the first problem is this week is dealing with steady flow energy equations, or you do an analysis over control volume. So the previous weeks we saw on control system, so where you have a closed system and you have system goes through under a process. So we saw how to calculate work, and we did an energy study and analysis of the control system. So similarly, we'll see how you apply it for a control volume. So in control volume, it's an open system. You have a mass which is coming in, it can go out. So your system, this thing will vary. So this can happen in two ways. You have a steady state and you have a unsteady state. In that unsteady state, your system will go through a change in in a certain period of time. But when it reaches steady state, the system will there will be not much change in the system. So that will remain same throughout the time. So we have problems on both. We'll see how to solve those. So it's in this control volume, again basically you do an energy balance. You see what are the interactions. You have some mass which is coming in and some mass which is going out. So this mass which is coming in will bring in some energy in terms of enthalpy, and which is going out will take away some energy. And then you have interaction with respect to the mass having kinetic energy or potential energy with which it is coming into the system, and similarly which it goes out. And also you have interaction based on heat. There can be heat transfer between the surrounding and the system, and also work transfer. So these are the major interactions with the control volume, and you balances this and you come up with a steady flow energy equation. And also there can be change with respect to time. In that you account also how much your internal energy of the system has, or energy of the system has changed with respect to time. So you write a dE by dt term to account for a change in system energy with respect to time in an unsteady case. So moving on, we'll see the first problem. We have a steam which is going through a pipe. So this steam is at a pressure of 1.4 megapascal and temperature of 300 degrees Celsius. So we have a steam pipe carrying steam at the specified 1.4 megapascal and 300 degrees Celsius. Now you are connecting this steam pipe to a vessel, so evacuated tank. So initially there is nothing inside, so evacuated tank. So you are connecting that through a valve. So this valve is opened and the tank is getting filled with the steam, and you are filling it till the pressure the tank reaches 1.4 megapascal. So it's coming in your pressures are equal with both the steam pressure in the pipe and the tank, and then the valve is closed. So the process takes place adiabatically, and kinetic energy and potential energies are negligible. So there is no kinetic energy, potential energy, you can take it as 0, and adiabatic, so there is no heat transfer happening. Determine the final temperature of the steam. Then you have a control volume is the tank, so as shown in the figure. So initial state in tank is evacuated, so there is no mass inside the tank. Then final state is pressure is known. So initial state of the steam pipe is also known, which is pressure and temperature, which is already given. So this process is a transient case. So you have fluid which is coming in, and your mass is getting stored in the tank. So your mass is varying with respect to time. So now if you write an energy balance across this control volume. So if you see initially the tank is assume for now the initial tank is at P1 V1, and M1 is the initial mass which is present, which is 0, and M2 is what is at the state 2. So QCV, some heat which is transferred across the this is a generalized equation. So we are writing a generalized case, and then we'll simplify it. So you have heat transfer QCV which is happening between the control volume and the surrounding, and then the energy which is brought in by the mass. So mass inlet into summation is the number of streams which is coming in. So for our case it will be single stream. So mi into hi plus vi square. Vi square is the kinetic energy processed by the mass which is coming in. Hi is the enthalpy, and gzi is the potential energy. So it's enthalpy is nothing but internal energy plus PV. PV is the boundary work which you have to do. So the mass which is coming in will come with some enthalpy Hi. This will be equals to the exit mass into exit enthalpy plus exit kinetic energy and potential energy. Similarly, this will be equal to, and the change in the energy of the system, energy of the control volume. So m2 into u2, internal energy, same potential energy and kinetic energy. This and the energy at the state 1, initial state. So m1 into u1 plus v1 square plus z1. So this is the energy possessed by the control volume at state 1 and state 2. So that difference is mentioned with the bracket CV. So this is the change in the internal energy, or you can say energy of the system. And then you have some work interaction which will happen between the system and the surrounding. So this is a your energy equation. So now in our case we know that there is no, because this is just connected across a valve, and when the valve is opened your fluid is coming in. So there is no, this being adiabatic, there is no heat transfer and there is no work transfer as well. So you are not getting any work or you are not giving any work. So there is no work transfer, and then initially your mass is 0. So initial internal energy also will be 0, and you are neglecting potential energy and kinetic energy. So substituting all this, your expression will come out to be mi hi, which is the inlet mass which is coming in, will be equal to m2 into u2. So m2 is the mass of the system at state 2, and u2 is the internal energy of the system at state 2. So this big equation has reduced down to this enthalpy which is brought in will be equal to internal energy of the system. So now we also know from continuity equation, you do a mass balance. So the mass which is coming in, because m1 is 0, there is no mass at initial condition. Your whichever mass is coming in is what is there at state 2. So mi is equal to m2. So that is also will get cancelled out. So what you are left out with is your enthalpy which is coming in is equal to the internal energy of the system at state 2. So hi will become equal to u2. So this being given is a steam, we can find out enthalpies and internal energy. So for steam at 1.4 megapascal and temperature of 300 degrees Celsius, your enthalpy is 3040.4 kilojoule per kg. So and we know the final pressure is 1.4 megapascal. So we know that your u2 is 3040.4 and your final pressure is 1.4 megapascal. So correspondingly you can find out what will be the temperature from the steam table. So corresponding to u2 equal to u equal to 3040.4 kilojoule per kg and pressure of 1.4 megapascal, you will get from the steam table that your temperature will be 452 degree Celsius. So if we see, initially the fluid steam was at 300 degrees Celsius. When you are filling it in the tank, your temperature has risen from 300 to 452 degrees Celsius. So that's an increase of 152 degrees Celsius. So is this clear? The other way is you can assume that gas to be an ideal case. In this case we know steam table. So other way is you have CPTI equals to U is CVT. We are assuming that at some condition datum is 0. So you can write CPT equals CVT. So you can from there you can find out the temperature at T2. That will be Cp by Cv into Ti. You can find that way also. But we know the properties here, and we can find it from the stream table in this given conditions. So next is moving on to the next problem. We have a 4 feet high and 3 feet diameter cylindrical water tank, so whose top is open to the atmosphere, which is initially filled with water. So you have a 3 feet diameter cylinder tank with a 4 feet height, and the top is open. So your top, the pressure is atmospheric pressure. So initially filled with water. So now the discharge plug near the bottom of the tank is pulled out. So basically you have a tap there at the bottom, you are opening the tap. So and water jet whose diameter is 0.5 inch streams out. So from the bottom your water comes out, and diameter is 0.5 inch. The average velocity of the jet is approximated as v equal to square root of 2gh. So where h is the height of water in the tank measured from the center of the hole. So your tap center and the water level, so that height is what height h is, and g is the gravitational acceleration due to gravity, and determine how long it takes for the water level in the tank to drop to 2 feet from the bottom. So initially 4 feet high, so when it comes to 2 feet, what time does it take? So this is a mass balance problem. We'll see how to solve this. So initially the conservation of mass relation for a control volume will be m dot in minus m dot out will be equal to mcv dt. So in this case, if you see, there is no mass which is coming in, so the water is filled already in the tank. You are just opening the tap to let the water go. So if you see, there is no inlet water coming in, but there is a outlet water, and your mass in the inside the system, control volume is the tank. Sorry, was I not audible from the start? Should I repeat the first problem? Sorry. Okay, I'll repeat the first problem. So, am I audible now, right?
Yes, sir.
Yeah, okay. So, we have a steam pipe. So, here we have initially a pressure of 1.4 megapascal, steam which is coming in, and you have a temperature of 300 degrees Celsius. So, this steam pipe is connected to a evacuated tank. So, you have an evacuated tank, and this is getting connected to the steam pipe through a valve. So, initially this tank has no mass. So, because it's evacuated, you have nothing inside the tank. So, you open the valve, now the steam is from the pipe flows through the valve to the tank, and it gets filled, and it reaches 1.4 megapascal. So, it reaches the steam pressure in the pipe. So, there will be no much mass flow rate later. So, when the pressures are equal, you close the valve. So, at this case, you need to find out what will be the temperature of the steam inside the tank. So, that's what the question is asking, and they are also saying that in the tank you have no heat transfer happening because this is insulated. So, it takes place adiabatically, so there is no heat transfer, and they are also saying that you don't have any kinetic energy or potential energy. So, now what all we know? We know that initially the tank, there is no mass, so m1 is 0. You know the final pressure of the tank, P2, which is 1.4 megapascal, and we know the steam inlet conditions. So what we'll write is a steady flow energy equation. We'll write a generalized steady flow energy equation. So first we'll see there can be so steady flow energy equation is nothing but you do an energy balance for the control volume system. So previously we saw control mass system in the previous week. So here we will see control volume system. So again, what all energy steady flow energy equation is energy equation balance. You see what all energy is coming in, what all going out, you balance it out. So you have heat transfer which can happen, you have work transfer which can happen, and you have mass which is coming in and which is going out. So this mass of fluid which is coming in will bring in some energy, and which is going out will take out some. And also, if it's a steady case, your system will not undergo any change, so its energy will remain same throughout time. But if it's an unsteady state, just like ours, if you see in this case, our tank initially was empty, and then it gets filled, and it reaches some pressure, and at that point your energy will be different. So in that case, we also need to account for the change in energy of the system. So how to write this? So we listed to the left side we have heat transfer, and then the energy brought in. So it's nothing but energy coming in is equal to energy going out. So that's what the expression signifies. So you have QCV. We assume the energy which is coming in is positive. So QCV plus Mi into Hi is the mass of mass which is coming in. So that has some enthalpy. So that plus it will have some potential energy and kinetic energy. So Mi into Vi square by 2 plus Mi into Gzi. So this is the mass which is coming in. So there is a summation sign to account for all the streams which are coming in. So you can have multiple masses coming in. So here in our problem there is only one. So but this being a generalized equation, there is a summation to signify that can have multiple inlets, and then this will be equal to the mass which is going out. So Me exit mass, and it will also have some enthalpy, potential energy and kinetic energy, plus the change in energy of the control volume. So M2 into U2 plus V2 square by 2 plus Gz2, that is the energy possessed by the system at state 2, so at the end of process, minus the energy at state 1. So M1 into U1 internal energy plus kinetic energy and potential energy. So this is the change in energy of the system for some time period, plus the work interaction which can happen. So this will be going out. So WCV is positive. So we have written plus WCV. So this is the generalized energy equation, energy flow equation. So now for our case, if you see, there is no, this being an adiabatic case, so there is no heat transfer, and next is there is no we assume that your potential energy and kinetic energy are negligible. So Vi square by 2 Gzi, you can assume it to be 0, and also we know that there is no mass which is going out. So exit Me will become 0, and we also know that inlet at state 1 there is no mass. So energy possessed by the tank at state 1 is 0. So substituting this in the general equation, it will reduce to Mi into Hi. It's the enthalpy of mass Mi coming in. This will be equal to M2 into U2, that is the internal energy of the system at state 2. Because internal energy at state 1 is 0, there is no mass, so there is no energy in the system, that is 0. This will be equal to M2 into U2, the energy at state 2, which is equal to the enthalpy which is coming in. So now if you apply a mass balance across this control volume, you will find out that the mass which is coming in Mi is the mass which is there in the system at state 2. So Mi will be equal to M2. So you can remove this Mi and M2. So this will become Hi equals to U2. So this being a steam, we know the conditions at which the steam is coming in, your 1.4 megapascal and 300 degrees Celsius. Using a steam table, so that's a table listing out all the properties at a specific given pressure and temperature, or you have list of values. You can find out corresponding to pressure of 1.4 megapascal and 300 degrees Celsius, your enthalpy will be 3040.4 kilojoule per kg. And now you know enthalpy, so that is equal to the internal energy of the system, specific internal energy U2. So now you know U2, you know pressure at which of the tank at state 2. So you know 2, so you can, from the steam table you can again find out what will be the corresponding temperature. So for 3040.4 of specific internal energy and pressure of 1.4 megapascal, you will find that your temperature is 452 degrees Celsius. So if you don't have, so this being a steam, you can find from steam table. If you had some other, we suppose air or something, you can assume that to be an ideal gas, and you can write HI as CPT and U as CVT. So this becomes CPTI equals CVT2. So you can find substituting the specific CP and CVs of the fluid, and you can find out the temperature. Here you know TI is 300 degrees Celsius, so you can find out T2 from that. So I hope this is clear. Okay, so moving on to the next question. We have a tank. So this tank is initially filled. So the tank dimensions are 4 feet in height and a 3 feet in diameter. So you have a 3 feet diameter tank and 4 feet height, and the top is exposed to atmosphere. So the top is your atmospheric pressure acting on the tank, and what you do is you have a tap at the bottom. So you have to open the tap, and they say there is a stream of water coming out which diameter is 0.5 inch, and you can find out the velocity at which the water is coming out is given as square root of 2 into G into H, where H is the height between the water layer, top layer, and the center of the tap. So that is the H, and G is the acceleration due to gravity. So they have asked to find out how much time will it take to drop from the 4 feet height to the 2 feet height. So this is a simple problem of doing a mass balance. Here if you see the mass coming in minus the mass going out should be equal to the change in mass of the system. Just like we did for an energy system, the energy which is coming in minus energy going out should be equal to the change in energy of the system. In a steady state, what will happen is change in energy of the system with respect to time will become 0. So it will become energy coming in will go into energy going out. Similarly, here mass coming in minus mass going out will be equal to change in mass of the system. And in a steady state, this mass flow which is in the system will become 0. So mass which is coming in will become mass is to going out. So coming to our problem, we have a tank. Here there is no water coming in, so the tank is already filled, and only thing is the mass is going out. So you have exit, so you don't have any inlet, so there will be change in mass in the system. That's what will happen. Your mass in the water in the tank will reduce. So M in minus M out will be equals to change in mass with respect to time. So we know that mass is nothing but rho into V into A. Rho is density, V is velocity, A is the area across which cross section. So for mass, the diameter of 0.5 inch, mass diameter of 0.5 inch, you can write the jet area of jet is pi d square by 4. So d is 0.5 inch, and h is will vary. So h will vary throughout the process. We will retain it as h. We know rho into root 2 gh. Jet is pi d jet by 4, and we also know that the mass in the tank is rho into the volume. So the volume of water in the tank. So the volume of water will change. So it can be expressed as the area of the cross section of the tank into height of the tank, h. So we'll substitute this 2 in the expression of the mass balance. So m in is 0. So m out is minus rho root of 2 gh into a jet equals mcv is rho into area of tank into h. So from here we substitute area of the tanks, and we simplify the expression. So we'll get dts here, this pi d square of tank by 4 will go out, so it will become dh by dt. So you take dt to the left side and the expression to the down, we'll get a simplified expression with respect to time. Dt equals minus d square of tank by d square of jet into dh by root 2 gh. So is a variable of t, and on the right side we have only variable h. So we can integrate this from time 0 to some time t, where your height is changing from initial height 4 feet to 2 feet. So when you integrate this, the expression is root of h naught minus root of h2 by root of g by 2 t, the ratio of diameter square. So this is the time which will take from going from height h naught to some height h2. So we know the values, so we substitute in. So h naught is 4 feet and h2 is 2 feet, and g is 32.2 feet per second, acceleration due to gravity in terms of feet. So substituting that, we will get 757 seconds. So this will come out to be 12.6 minutes. This problem is given in feet, so but the procedure will remain same irrespective. So you can convert that into meters and substitute feet to meters, and inch to again meters. You can substitute that and solve it, or you can substitute directly g in terms of feet and can solve it. So time you will get is 757 seconds. It will come out to be 12.6 a minute. So it will take 12.6 minutes for the tank to reach from 4 feet to 2 feet. So it will become half emptied at 12.6 minutes. So is this clear?
Yes, sir.
Okay. So moving on, we have a steam is leaving a 4-liter pressure cooker whose operating pressure is 150 kilopascal. It is observed that the amount of liquid in the cooker has decreased by 0.6 liter in 40 minutes. You have a so you have a pressure cooker. So they are saying it's of 4-liter capacity, and the operating pressure in that is 150 kilopascal. So in 40 minutes time, you observe that the water inside has reduced by 0.6 liters after the steady operating condition are established. So your inside pressure and temperature are the same, it's not varying with respect. So that's what they mean by steady operating condition. And the cross sectional area of the exit opening, so you have that vessel at the top, the pressure cookers, so from where you steam is let out. So that opening is of cross sectional area of 8 millimeter square. So now we have to find out the mass flow rate of the steam and the exit velocity, the total and flow energies of the steam per unit mass. Third is the rate at which energy leaves the cooker by steam. So this is the three values which you have to find. So we'll see, and they have given some properties for the steam. So you have saturated liquid water and water vapor at 150 kilopascal. You have specific volume given for saturated liquid, which is 0.001053, and specific volume of steam gas is 1.1594, And similarly for internal energy of steam and enthalpy of steam is given. So now we'll know. So in the pressure cooker, so you have reached steady state. So at that condition, so you saturation condition will exist. So because it's boiling at there is a phase change, so it will happen at at constant temperature for the corresponding to the pressure inside the cooker. So pressure cooker, the pressure is 150 kilopascal. So that's what is given. So your mass which you are losing in 40 minutes time. So we'll first find out that. So you know they say that you are losing 0.6 liters of water. So 0.6 liters, and you know the because this is at saturated condition corresponding to 150 kilopascal, and we know the specific volume of the liquid at that point as 0.001053. So specific volume is nothing but your volume by mass, or inverse of density. So mass can be calculated from the change in volume, the volume by specific volume will come out to be 0.6 liters by 0.001053, and we are converting liters to meter cube. So we'll multiply by 10 power minus 3, so yeah, divided by 1000, so will come out to be 0.57 kgs. Here it's in liter, you have to convert it into meter cube because your specific volume is in meter cube per kg. So 1 meter cube is 1000 liters, so that's why divided by 1000. So it will come, your mass amount of water which you are using is 0.57 kgs. So now the mass flow rate, this is the total amount of mass which you are losing in the period of 40 minutes. So what is the flow rate of the steam which is coming out? So that is equal to the mass, total mass divided by the total time it has taken. So 0.57 by 40. So this will come out to be 0.0142 kg per minute. So this is the mass of steam which is coming out per minute, and this is equal to 2.37 into 10 power minus 4 kgs per second. And then we have to find out the velocity at which the steam is coming out. So that was the first one. The first one is the mass flow rate of the steam. So we have found out mass flow rate. Now the exit velocity. So exit velocity is nothing but, so m dot will be rho into area into velocity. So density we know. So the steam which is coming out of the vessel is in saturated steam, so saturated vapor. So the density is corresponding to the saturated vapor, and then area cross section of the opening is known, is 8 millimeter square, and we also know the mass flow rate. So m dot is m dot by rho a. So 1 by rho is nothing but specific volume. So you can write m dot into specific volume of saturated vapor divided by area of cross section. So substituting all the values, we will find out that the velocity of the steam which is coming out is 34.3 meters per second. Okay, so we have solved the first part. So we'll see the next one. So next one is the total and the flow energies of the steam per unit mass. So you know enthalpy is U plus PV, assuming that your kinetic and potential energies are negligible. So the flow energy is nothing but enthalpy contains two parts, your internal energy and the flow work. So you need to just find out flow work. So that is PV, that is the flow energy. So you can find it by H minus U. So enthalpy minus internal energy. So it will become, you know, at that 150 kilopascal, your enthalpy is 2693.1. That is enthalpy of the saturated vapor which is coming out, and internal energy is 2519.2 So the difference of these two will give you the flow energy required. So that will be equal to 173.9 kilojoule per kg. And the next one is to find out the total energy which is going out of the steam. So that is nothing but your enthalpy, because we are assuming your kinetic energy and potential energy are zero. So the energy which is going out is nothing but m dot into enthalpy. So here we have been asked per unit mass, so that is specific energy. So we don't multiply by mass, we will not multiply by mass, because it's asked per unit mass. Per unit mass is specific enthalpy or specific flow energy. So here this total energy which is going out is will be equal to the enthalpy, which is 2693.1 kilojoule per kg. So why are we assuming kinetic energy and potential energy is zero? So potential energy is zero. If you see kinetic energy is specific kinetic energy here. So v square by 2. We have already calculated velocity. If you substitute that, you will find that your kinetic energy is 0.588 kilojoule per kg. So compared to your value to 2693.1, 0.588, 0.6 is negligible. So that's why we assume here your kinetic energy and potential energy are negligible, and you can directly use the enthalpy values. So unless if you go at having nozzles and very high velocities, so in that case you have to find the kinetic energy will be significant. So but in these cases you can neglect the kinetic energy and potential energies. So the third part of the question was,
Excuse me, sir.
yes,
Sir, I have a small doubt in. Could you please move
yeah,
to
yeah,
next slide?
yeah, let's go ahead. Next one. Okay, yeah,
Sir, in calculating m, you have taken Vf, and in calculating velocity, you have taken Vg. Could you please explain that?
yeah. So initially you assume that initially the cooker is with you fill it with water. So you have lost initially you filled it with 4 liter of water, that you have lost 0.6 liters. See, steam is leaving a 4 liter pressure cooker whose operating pressure is 150 kilopascal. It is observed that the amount of liquid in the cooker has decreased by 0.6 liter. So in this case, in the problem, they are measuring the liquid in the pressure cooker. So previously they said it was 4 liter. They observed that in 40 minutes the liquid volume has gone down by 0.6 liters. So if they would have said in the problem it was the vapor, it's because the volume of liquid is easier to measure. You can see directly in the liquid the height which is going down. You can easily measure the liquid. It's very difficult to measure the vapor. So in the problem it's been mentioned that the liquid volume is going down by 0.6 liter. So we have used the specific volume of the liquid. But this 0.6 liters of liquid which is converted to steam, that steam is going out of the opening, the vessel in the pressure cooker which you see, the vessel which is coming out is the steam which is coming out. So that steam which is coming out, you are finding this mass which is getting converted to vapor, that will come out. So you are calculating mass flow rate using saturated vapor condition, because now it has already been converted to vapor and that is coming out. Is this clear?
Okay, sir. Understood, sir.
Okay.
Yes, yes, yes.
So we have seen second part. The third part is you need to find out the rate at which the energy is leaving the cooker. So the rate at which energy is leaving the cooker is nothing but in the first case you found out the total energy, which was specific total energy which is going out. The third case you are finding the rate at which, so you multiply it with mass. So m dot into the energy which is going out. So m dot we already calculated, it's 2.37 into 10 power minus 4 into the enthalpy 2693.1. So which will come out to be 0.638 kilojoule per second or kilowatt. So 0.638 kilowatt is the energy of energy carried by the mass which is going out. Okay. So moving on, I hope this problem is clear. You have any doubts? Okay. So going on to the next problem, uh, we have a insulated mixing chamber. So you are mixing two fluids. So one is steam, which is at 10 bar and 460 degrees Celsius. This is getting mixed with liquid water, which is at also at 10 bar, but your temperature is 45 degrees. So now basically you are mixing liquid and water and steam, which are at different temperatures in a mixing chamber, and then you are taking away some the mixture of this, which is coming out at saturated liquid, which is a saturated liquid corresponding to 10 bar. So that is the exit condition, and inlet conditions is 10 bar 45 degrees for water, 10 bar 460 degrees for your steam. So in this case they are asking to neglect kinetic energy and potential energy. We need to find out the ratio of mass flow rates of the incoming streams. So your steam is coming in, which is at higher energy, so that will supply that energy to the water. So this cannot be you cannot put it equal, so you have to mix it in certain ratio such that your after the mixing chamber, when you take it out, you see that the liquid which is coming out is at saturated liquid condition. So what is the ratio? So that's what is been asked. So we know, so we do an energy balance across this mixing chamber. We see what is coming in is the M1H1 is the steam, and M2H2 is the water which is coming on, and which is going out is the saturated liquid at 10 bar M3H3. So M1H1 plus M2H2 minus M3H3, and next is we have one equation, but we have three unknowns. We don't know mass 1, M1, M2 and M3. You know M3 now doing a mass balance, you can find out that the mass which is coming in should be equal to the mass which is going out, assuming this is a steady state. So M3 equals M1 plus M2. So we are substituting M3 as M1 plus M2. We'll get the ratio of M1 and M2 as H3 minus H2 by H1 minus H3. So this is the we use the first two equation to come up with this ratio of mass flow rate which is required. So in terms of enthalpies. So now we know all three conditions of the fluid. So we'll go back to the steam table. We'll get the values. So for water at 10 bar and 45 degrees, and 10 bar 460 degrees Celsius for steam, and saturated liquid enthalpy for at 10 bar. So from steam table, H1 is 3392.2 kilojoule per kg. So now state 2 is a compressed liquid state. So we know at H2 of 10 bar and 45 degrees Celsius, we can find out using your internal energy plus P into V. H is U plus PV, right? So H you can find out, you can find internal energy at 45 degrees Celsius plus pressure is 10 bar. So 10 bar into Vf 45 degrees Celsius. Okay. Here we have written 1000 because we are converting into kilopascals. So it will come out to be 189.42 kilojoule per kg. We are converting kilopascal because we are finding all enthalpies and internal energy in terms of kilojoule. So that's why we are putting pressure also in kilopascal. So we will get enthalpy at state 2 as 189.42 kilojoule per kg. State 3 is saturated liquid water, so at 10 bar. So we can find directly for 10 bar your H3 is 762.8 kilojoule per kg. So when you substitute all three enthalpies here in the expression, you will get M1 equals 0.2181 is the ratio. So if you take 1 kg of liquid water at 10 bar and 45 degrees Celsius, you will require 0.2181 grams of steam at 450 degrees Celsius. So that's what this will mean. So is this clear?
Yes, sir.
Okay. So moving on to the next problem, we have a refrigerant R134A which is compressed steadily in a compressor. So now we have come up, we'll see how to do an energy balance across a compressor. So we have a compressor, so it's operating between 140 kilopascal and 700 kilopascal. So your corresponding temperatures are -10 and 120 degrees Celsius. So your pressure and temperature at the inlet and outlet is given. They have also given volumetric flow rate. So at the inlet is 0.06 meter cube per minute. They are saying that the heat loss to the ambient is 7% of the input power. So they are saying the compressor is losing some heat to the atmosphere, and they are saying that fraction of heat which is lost to the ambient is 7% of the input power. So determine the power required. It's what we have to find, and they say also saying that you neglect kinetic energy and potential energy. So this being a compressor, and it will run, you have, if there is no energy accumulation or reduction in the compressor, it will be a steady flow. So apply steady flow energy equation. So your Q which is coming in or work, it will be equal to work plus your interaction with respect to enthalpies. So you have M1 H1 which is coming in, M2 M H2 which is going out. Your mass flow will remain same, because a steady flow which is coming in which will go out. So plus Q, the heat interaction which is going out, so going out is positive, minus W because work which is coming in is negative. This will be equal to 0. So here in the problem they have given that volumetric flow rate is 0.06 meter cube per minute. So we know, we can find out the mass flow rate. So at suction we know your pressure is 140 kilopascal and your temperature is -10 degrees Celsius. So corresponding to this conditions, from refrigerant chart or a table for R134A, we can get your specific volume is 0.1461 meter cube per kg, and correspondingly you can find out both enthalpy and at inlet and exit for the given pressure and temperature conditions. So which is given here, H1 is 246.4 which is the inlet enthalpy, and H2 is 358.9 which is the exit enthalpy. So we can now find out mass flow rate. We know the volumetric flow rate, we also know the inlet specific volume. So 0.06 divided by V1, the specific volume at the inlet, which will equal to 0.4107 kg per minute. So we have found out mass flow rate, we know the enthalpies. So and we also know that Q is 7% of input power. So Q is 0.07 W. So that substituting here in the expression and substituting all the enthalpy values, we will get we will get W as 49.68 kilojoule per minute. So is this clear? You have the first thing is you have to find out the mass flow rate. If you have found out mass flow rate, you can find out the enthalpies, you can substitute there, and Q they have already given a fraction of 7% is the work done of the work done. So this will be 0.07. So my Q is 0.07 and W, yeah, the inlet is coming in negative, so Q minus W. So minus 0.07 into work plus work will be equal to plus your mass into the enthalpy difference. Substituting this, we can solve for W. It's only variable here, so it will come out to be 49.68 kilojoule per minute.
Sir,
Yeah,
from which book you are taking problem?
it's from multiple books. It's not a single book.
Okay, okay. Okay.
Okay. So we have next problem. You have a tank containing 45 kilograms of liquid water initially. So we have a tank. In this tank we have 45 kg of liquid, and at 45 degrees Celsius, this is 145 degrees Celsius. Yeah, it is at 45 degrees Celsius. It's not 458. I will make correction here. Has one inlet and one exit with equal mass flow rates. So mass flow rate is equal, which is coming in is also going out. So the liquid water enters at 445 degrees Celsius and a mass flow rate of 270 kg per hour. A cooling coil is immersed in the water, which removes energy at a rate of 7.6 kilowatt. So the water is well mixed. So you have a cooling coil which is going in the tank, and it's removing energy at 7.6 kilowatts, and there is mass of water which is coming in, liquid which is coming in. It's at 270 kg per hour at 45 degrees Celsius, and you also have a paddle wheel which rotates to make the temperature uniform in the tank. So the power input to the water from the paddle wheel is 0.6 kilowatts. So you know the work done in the paddle wheel. You also know the heat transfer occurring between the cooling coil and the water, and the pressure at the inlet and exit are all equal, and you can neglect the kinetic energy and potential energy. So now we have to find and plot the variation of this water temperature, the water in the tank, the temperature of the water in the tank with respect to time. So how it will vary. So we'll see how to solve this. So we'll go back again to the energy equation. So you see the Q heat transfer happening minus W plus m dot into H1 minus H2 is the enthalpy change of the fluid which is coming in and going out. This total will be equal to change in the internal energy of the system. So for steady state, in the previous problem which we saw, this was a steady state for the compressor. So this du Cv by dt was becoming 0. In this case, your temperature in the tank, the water in the tank is varying. So the internal energy will not be same. It will be varying with respect to time. So we will take du Cv by dt also into account. So m dot is the mass flow rate which is coming in, which is given 270 kg per hour, and we know the enthalpies of the fluid which is coming in and going out. Going out is the temperature corresponding to the liquid tank. So you have a you see in this figure, you have a tank, there is water. This water initially is at 45 degrees Celsius, and you also putting in some water which is coming at 45 degrees Celsius, but there is a cooling coil which is removing heat from the tank, or you can say it is cooling the tank. So your temperature should go down from the tank. So this paddle will make sure that the tank is uniform, it's at a uniform temperature. So the whole of water in the tank will be at some temperature, and that is the temperature at which the fluid will leave. So now we can express du Cv by dt as U is nothing but m dot into specific internal energy. So CV is the tank mass of water in the tank, mCV into U by dt. So you can take a mass out, mCV du by dt. You can take mass out because your mass in the tank is not changing, because whatever mass of fluid which is coming in is also going out. So the mass in the tank is not changing. If you write, you can write a mass balance equation. You will come out with mCV will be equal to constant. So change in mass in the tank will be 0. So you can take mCV out. So mCV equals du by dt. So now du by dt, this small t is corresponding to time. So you multiply du by capital T into dt by dt. You apply cyclic rule here. So we know du by dt is nothing but your constant volume specific heat Cv. So C into dt by d small t with respect to time. So you can express this change in internal energy of the water in the tank as mass into specific volume into change in temperature with respect to time. So that we substitute in the energy equation, and we know that your H is nothing but C into T, m dot into C into T1 minus T. T1 is the temperature at which the fluid is coming in at state 1. This T is the temperature of the water in the tank which is going out. So that will vary with respect to time. So we are assuming the variable T there. So now we know Q dot Cv, we know W dot Cv. When you integrate this, you will end up with this equation for temperature. This T equals C1 exponential minus m dot by mCv T plus the Q dot Cv minus WCv by m dot C plus T1. You just divide it by m dot Cv and divide by T1 minus T there in the other side. So you can get and you have to integrate that. So we will end up with this equation. So if you differentiate this, you can see easily that you will get the above equation. So substitute, we know all the values here. So now we have to find out a constant C1. So we know at initial start of the process, your temperature is equal to 45 degrees Celsius at time t equals 0. So we substitute that and we can find out C1. So when we find C1, we substitute that direct C1 in the expression, and we substitute all the other values. So m dot we know m dot is 270 kg per hour, and the mass of water in the tank is 45 kgs. And we know also the heat which is taken from the fluid is 7.6 kilowatts, and paddle wheel is 0.6 kilowatts. So we substitute that, and C of water is Cp of water is 4.2 kilojoule per kg Kelvin. So substituting all, we will end up with a simpler equation. T is 318 minus 22 to 1 minus exponential minus 60. So if you see, there is an exponential decrease in temperature. So initially it was at 318 degrees. So it's exponentially decreasing, and when T becomes infinity, so this will become equal to 296. So is this clear? So moving on, the next problem is we have an electronic component of a computer which are cooled by air flowing through a fan mounted at the inlet of the electronic closure. So here in the figure we see that there is electronic component in the closure. So at down there is air in, there is a fan which is pushing some air inside and it's cooling the electronic components, and it's exiting from state 2. So at steady state air enters at 20 degrees Celsius at 1 atmosphere. They are saying for noise control the velocity of the air in entering air cannot exceed 1.3 meters per second. So this will limit how much air which can go in. So that is limited by the fan speed and noise. So velocity, maximum velocity of air is given as 1.3 meters per second. They are also saying that for temperature control, the temperature of the air at the exit cannot exceed 32 degrees Celsius. So your exit condition outlet is given. It cannot exceed 32 degrees Celsius. So maximum temperature it can go is 32. So because if your temperature is more at the exit, means your electronic component temperature itself is high. So you don't want that. So you are limiting, saying that your air should be as 32 degrees Celsius. So you are making sure that you have mass, a good amount of mass of air which is going out to cool the electronic components. So your exit is 32 degrees Celsius, and they are saying the electronic component and fan receive respectively 80 watts and 18 watts of electric power. So electronic component you have 80 watts, and fan you have 18 watts of energy coming in. So determine the smallest fan inlet area in centimeter square for which the limits on entering air velocity and exit air temperatures are met. So you need to find out the inlet area, or ultimately the mass of air. From there you need to find out the area opening, because you know the velocity for which your both velocity of air entering in and 32 degrees Celsius temperature going out is met. The Cp of air is given as 1.005 kilojoule per kg Kelvin. So we'll see how to solve this. So area we can find by m dot into V specific volume by velocity. So m is nothing but rho av. So can express in terms of specific volume here. So this is, from this we can find out area. So for this now we need to find out mass. So we apply because this will go in a steady flow energy equation. There is a steady flow of air going in. There is no air getting accumulated inside the closure. So it's a steady state process. So we know Q dot Cv. There is no heat interaction. They are saying there is no heat interaction with the environment, but you are supplying in some work to both the electronic component and the fan. So you know how much work which is going in, and you neglect both kinetic energy and potential energy. So you have mass of air which is going in, and some mass of same amount of mass of air which is going out. So m dot h1 minus h2. So removing both Q and potential kinetic energy, will end up with your work done will be equal to the change in enthalpy of the air which is going in and going out. So we know the amount of work which is giving in is 80 watts for the electronic component and 18 watts for the fan. So your total 98 watts of electrical power is given in to the cooling closure. So from here we know enthalpy difference is Cp T1 minus T2. So if you take it to the other side, so m dot is minus W by Cp T2 minus T1. So from this you can substitute mass in the above expression for area. So substituting that, you will get 1 by V1 into minus W by Cp T2 minus T1. So here specific volume, we don't know the specific volume of air, so we will go to the ideal gas equation. So ideal gas equation is P equals PV equals to nRT or MRT. That will simplify, it becomes P specific volume equals to R into temperature. So you substitute you know R, you know temperature and pressure, so you can substitute that and find out the area. So for the so we know velocity, so the limiting case is 1.3 meters per second, and your work is 98 watts, Cp is 1.005, and your temperature difference, inlet is 20 degrees Celsius, so 273 plus 20, 293, and exit is 32, so 273 plus 32, so 305, and this is in kilojoules, so multiply by 10 power 3 1000 to convert it into joules, and here it's RT by pressure. So pressure is 1 bar, 1 atmosphere, so 1.01325 into 10 power 5 Newton per meter square. R is universal gas constant is 8.314 kilojoule per kg. So you divide it by the molecular weight to get the gas constant for air. So 8314 divided by 28.97 into temperature of air coming in is 293 Kelvin. So substituting this, you can find out the specific volume, and we are converting this to centimeter square. So this the calculation is made in meter square. So multiply by 10 power 4 to convert it into centimeter square. So this will come out to be area should be greater than or equal to 52 centimeter square. So if the area is small, that is the limit. The area is 52 centimeter square. So that will make sure your velocity is 1.3 meter square, 1.3 meters per second, and your exit temperature is 32 degrees Celsius. But if your area increases, then your velocity will go down, but your for the same mass flow rate, your velocity will go down, but your temperature also 32 degrees Celsius you can come down, or for a given same velocity of air coming in, you can bring down the temperature. So your area should be greater than or equal to 52 centimeter square. Any doubts? Okay. So moving on, we have a steam which enters at a converging diverging nozzle. We have steam which enters at a converging diverging nozzle. This is operating at steady state. So steady state they have given with pressure of 40 bar and temperature of 400 degrees Celsius and a velocity of 10 meters per second. So your inlet condition is known. So you have 40 bar, 400 degrees Celsius and 10 meters per second. So now the steam flow.
Sir, it is a steady flow energy equation problem?
Yeah, it's a steady flow energy equation problem.
Okay, okay, okay.
So they have given already in the it's in the steady state. So here whatever is coming in, it's also go out. So your pressure is changing in the nozzle from 40 bar to 15 bar, and your velocity which is coming in is 10 meters per second is going out at 665 meters per second. This nozzle is insulated, so there will be no heat interaction with the surrounding, and there is also no work given into the nozzle. So basically there is a change in cross sectional area, your fluid is coming in, you are reducing pressure but you are increasing the velocity at the exit. So the same condition for the steam is plotted in a TV diagram. So we have state 1 which is at 40 bar and 400 degrees Celsius, and state 2 which is at 15 bar. So similarly in this case we have to find out the exit area of the nozzle. So mass flow rate is also given 2 kg per second. We'll see. similar, just like the previous case, we can find out area rho AV expressed in terms of m dot v2 by specific volume by your velocity. So you write a steady flow energy equation. The nozzle is insulated, so there is no heat transfer, so heat transfer is 0. There is no work transfer, so work transfer is 0. You have some enthalpy of fluid coming in, and with some velocity is given. So here potential energy is 0, so it's at same height, so your potential energy is 0, and it's going out with some enthalpy and some velocity. So this expression can be simplified into writing your change in enthalpy is equal to the change in kinetic energy. So H2 equals H1 plus V1 square minus V2 square by 2. So from this we can find out, we know enthalpy from this being a steam, from steam table corresponding to 40 bars and 400 degrees Celsius, we will find out that enthalpy is 3213.6 kilojoule per kg. So you know enthalpy 1, you know velocity at state 1, you know velocity at state 2. Substituting this, we will find out that this is 10 meters per second, V2 665 meters per second by 2. This will be in joules, so divide by 1000 to convert it into kilojoules. So this will become H2 is 3213.6 minus 221.1. This will come out to be 2992.5 kilojoule per kg. So if you see in this problem, your kinetic energy is significant. It's a 221 compared to the previous one problem in the pressure cooker. There the kinetic energy was negligible. So here your velocity is very large and it has a significant amount of energy. So now you know the enthalpy at exit. So corresponding to 15 bar and this enthalpy, from steam table we can find out the specific volume. So specific volume will be 0.1627 meter cube per kg. So substituting this, we know mass of fluid which is coming in m dot, which is 2 kg per second. Specific volume is 0.1627 and divided by your velocity is 665 at exit. So we can find out area is nothing but 4.89 into 10 power minus 4 meter square. So this is the area you require for to reach 665 meters per second velocity. Okay, let's see. Moving on to the next problem. Any doubts on the previous one?
No, sir, everything is okay.
Okay. So moving on, we have a tank which is an insulated rigid tank which has a volume of 1000 liters. This air is initially at 1 megapascal and 300 Kelvin. So you know the conditions, your volume is known 1000 liters, you know temperature which is 300 Kelvin, you also know the pressure is 1 megapascal. You have a valve at the top to this rigid vessel, and they are saying a valve on the top is now open and the air is allowed to escape slowly into the atmosphere until the pressure in the vessel reaches 100 kilopascal, at which point the valve is closed. So initially the pressure in the tank is 1 megapascal, your valve is open, you are leaving the air to escape, and you are closing when the pressure in the vessel reaches 100 kilopascal, that is 1 bar. So the temperature of the air inside the tank is maintained constant during this process by an electric resistance heater. So you have a heater here which will make sure that your temperature inside the tank is constant, which is 300 Kelvin. So now we need to find what is the amount of mass of air that has escaped. B, the electrical work done during the process. You can assume the kinetic energy and potential energy is 0. So again, we can directly find out the mass. We know initially, we know the volume of the vessel, we know the pressure and temperature. At state 1, its pressure is 1 megapascal, your volume is same 1000 liters and 300 Kelvin. Even at state 2, again the volume will be same, you are maintaining the temperature, so your temperature is also same, but your pressure is decreased from 10 bar to 1 bar. So we will write an ideal gas equation. So PV equals MRT. So you can write mass as PV by RT. So in this case, your volume and temperature are constant. Your gas is same, so your R is gas constant is same. So M1 minus M2. So mass at state 1 minus mass at state 2 is equals to V by RT into change in pressure. So change in pressure, you know, volume 1000 liters. So convert into meter cube. So there will be 1 meter cube divided by R for air. So 8.31 divided by 29.84, and temperature is 300 Kelvin, and you know pressure 10 bar minus 10 bar minus 1 into 10 power 5. So substituting that, you will find out that the mass which is escaped, say M1 minus M2 is nothing but the mass of air which has gone out of the tank. So this will be equal to 10.4 kgs. So we straight away found out the change in mass to find out the mass which has escaped. Now we'll apply an energy balance to find out how much of electrical energy which is supplied to the heater. So we are neglecting kinetic energy and potential energy. So the change in energy of the system is nothing but change in internal energy of the system. This will be equals to the work which is going in and the energy taken by the fluid which is going out. So minus Wx minus m dot E into He. So this will be simplified expression which you will get from the energy flow equation. So this being an unsteady case, you can write the change in mass of the system dmCV by dt as minus m dot E. So that is the change, your mass flow rate of the exit stream or the exit air which is going out will be equal to the change in rate of change of mass in the system. This is the mass. This you will get from the mass balance equation. So substituting this, you know, He is dm. We are substituting m dot E as dmCV by dt. So since the exit enthalpy is equal to the enthalpy of the fluid in the tank, so and the tank is at constant temperature, so H is nothing but Cp into temperature of the control volume. So this is the enthalpy of the exit stream or exit air. So we substitute that for enthalpy, and the dmCV by dt is nothing but your change in mass in the system. So you substitute m2 minus m1, and your change in internal energy is dUCV by dt is m2 u2 minus m1 u1. So substitute that. So we have already calculated m2 minus m1, and we can also calculate separate m2 and m1 using the same ideal gas equation P2V by RT. So substituting that, and internal energy you can find it by Cv into temperature. Here enthalpy you are using Cp into T, internal energy you are using Cv into T. Substituting that, you can Cp is known 1.005, Cv is 0.718. So you substitute that, and you can find out the other values are all known. Pressure is known, volume is known, temperature is known, R is known. R is Cp minus Cv. So you can substitute that. From this you can find out the work which is supplied to the heater to maintain the constant temperature. So this, when you simplify it, it will become W is V into P2 minus P1. This whole expression can be simplified into V into change in P2 minus P1. Why this is happening? Because if you see this whole process is a isothermal process, constant temperature process. So your work done, which is nothing but V into change in pressure. So we ended up from top all the way to a simplified expression V into P2 minus P1. So this will come out to be minus 900 kilojoules. So any doubts? Okay. I think this is the last problem which I have. Okay, so we consider so now we have a reservoir compressed this thing. You want to fill air into your car tire. So it's a problem regarding that. You have a tire of the car wheel, so you are considering a single wheel. So in that wheel you have force F or load F which is being applied on the
Sir, figure please.
yes.
Just at a glance, the figure is required.
Yeah. Okay. So from the figure we will see.
Okay.
Okay. So you have your tire. So and this is the uh, rim, and the bottom is the tire which is getting inflated. So you have a reservoir, compressed air in a reservoir. You are connecting it through a hose to the wheel. So now your air is getting filled inside the tire, and this is getting inflated. This tire is subjected to a load F. So your car is of some weight, so it will put in weight on the tires. So this weight is F, which is given as 3000 newtons, and filling the air, your the tire is getting inflated, and this car is getting lifted by the or wheel hub is getting lifted by 0.2 meters. And you have atmospheric air which is subjected on the tire, and they have given that atmospheric pressure is 1 bar and the reservoir pressure is 5 bar at 20 degrees Celsius. They have also given your volume initially is at 0.02. At the after filling in air, your volume is 0.03 meter cube. So what all else is given? The reservoir pressure is PR/TR. During inflating process, the thermodynamic state of air inside the tire tube goes from initial state 1 to 2. So we know that state points of 2. The wheel hub is raised by height delta h. The assumption which they are making, they are saying that the thermodynamic state of air contained in the reservoir remains constant. So reservoir means same. Your the property of the reservoir will not change. So it will have pressure PR and TR. The second assumption is the volume of air contained in the pipe connecting the reservoir and the tire tube is negligible. So the reservoir is connected to the tire by a hose. So this you are assuming that pipe has negligible amount of air. The third is the strain energy of the tire is neglected. So you are not taking into account because the tire initially was flat. Now when it's expanding, it will have some strain energy across the tire, right? So you are assuming that all is neglected. There is no heat transfer across the tire, and they are saying the potential energy is negligible. You can consider air gas perfect gas. So your Cp is constant. That's what they mean. So you need to find out the mass of air which is going in to the tire, or it is taken from the reservoir. So delta m you need to find out. So they have given your state points of the tire. Initially volume is 0.02 at 1.5 bar. After inflating, it is at 0.03 and 3 bar. So atmospheric pressure is 1 bar. Your reservoir pressure is 5 bar. Your gas constant specific is given as 0.288, and similarly CV is given 0.7205. Load on the tire is given as 3000 Newton, and the elevation of the hub is given as 0.2 meter. So this all is known. So we'll see how to solve this. So you see, again, this is not a steady state equation. This will be change in it's an unchecked problem. So your duCv, the previous expression. So duCv equals minus w plus m dot into h. So that's the same equation which will come. So here the change in internal energy after at point 1 and point 2, there will be same change in internal energy. So that will be equal to the work done plus your mass entering is the change in mass in the reservoir. So the delta m. So that will be equal to the change in mass in the system. So that amount of mass is entering into the tire. So m2 minus m1 into hr. So what is the work done in the system? So here your work done is because you are pushing air inside the tire. So the tire is doing work. So the tire is lifting the load by 0.2 meter. So that is one work. The other work is it's getting expanded. So now it will do some work on the surrounding. So PV work, P into delta V. So that amount of work is done in pushing the tire, inflating, pushing the atmospheric pressure which is on the surface of the tire. So that is the opposing force which is happening. So you have F and the pressure. So you have to overcome this both. So that is the work done. So minus F into delta H minus atmospheric pressure into change in volume. So this is the total amount of work which is being done by the tire. So now substituting this in the expression, your delta U is nothing but internal energy at state 2 minus state 1 m2 into U2 minus m1 into U1. This will be equal to minus F into delta H minus PA into delta V plus m2 minus m1 into enthalpy of the reservoir, because the air which is coming into the tire will possess the same enthalpy which is there in the reservoir, right? So m2 minus m1 into enthalpy of at the reservoir. So you know U2 is you can express as Cv into T. So m2 Cv T2 minus m1 Cv T1. We are taking this both work done to the left side. So it become F plus F into delta H plus PA into delta V. So m2 minus m1 is what we need to find. So that will be equal to delta m into Cp T. So for enthalpy. So here Cv you can take it common. So and we are multiplying and divide by R. So Cv by R into m2 R T2 minus m1 R T1 plus same. So m2 R T2 you can use an ideal gas equation to express this as pressure into volume. So PV equal to MRT. So you are writing this as P2 V2. So minus P1 V1 into Cv by R plus F delta H plus PA into V2 minus V1. This will be equal to delta M into CPTR. So from this we can straight away find out delta M. We are substituting Cv which is given 0.7205, R 0.2882. Your pressure at state 2 is 3 bar, volume is 0.03. Your pressure is 1.5 at state 1, V1 is 0.02. This is given this table. And multiplying by 10 power 5 to convert pressure which is in bar to Pascal. Then 3000 is the load which is which the tire is subjected to, into the elevation 0.2 meters plus atmospheric pressure which is 1 bar, so 10 power 5 Pascal, into change in volume V2 minus V1. So 0.03 minus 0.02. This will be equal to the change in mass into Cp. Cp is Cv plus R. They have given Cv, they have given R. So you can add this up to find out Cp. It will come out to be 1.0087 into your temperature of reservoir. So that is 20 degrees Celsius. So 273.15 plus 20, which is 293.15. I can take 273 also. So dividing it by CPPR, we will find out that your mass which is coming from the reservoir to the tank is equal to 56.138 grams. So this is the amount of mass which is taken from the reservoir to fill the tire. Is this clear? Any doubts?
No, sir.
Okay. I think this was the last problem. If you have any doubts, you can ask, or else we can close the session.
Thank you, sir.
Okay. Thank you. Okay. Thanks for joining.
Okay, sir. Good night, sir.